All right, so I asked you all to basically set up all the files for this RStudio project. So your file structure should look like something like this, where you have the 10 stability validation project. And then if you go on code, you can go ahead and launch this partial code here. And today, our goal is going to be to basically, so just to kind of give a quick recap of everything we've done. So we had 3 years of yield monitor data that we wrangled, cleaned, and interpolated, right? We used those three interpolated yield monitor data to create spatial temporal stability classes and exported that to file. Then we brought in the terrain exercise where the primary terrain variable of elevation, we interpolated that and used that raster to calculate slope, aspect, flow direction. Then we also brought in the soil electroconductivity layers and then used both the shallow and deep soil EC, interpolated those and also exported to file. So now today, the goal of today's exercise is going to be to import all of those processed data layers that I just talked about, spatially join them into a single object, and then we're going to basically validate our spatial temporal stability zones using the terrain and the EC data for this field. So the questions we're gonna be asking in the end is there any relationship between these terrain and EC data layers with the zones that we identified in this data sets, right? And those zones, again, zones based on yield data only. That was our first zoning approach, was to create zones of yield stability in space and time. So today we're going to be validating those zones using all these layers that we processed already. I guess before we get started with that, any questions or thoughts? All right. I don't hear anything, so let's move on. So the first thing, as always, is just us loading the packages. I think all these packages you already have. I believe Forcats is part of Tidyverse, so if you install Tidyverse, you should have it. But anyways, go ahead and run this chunk, and I'm assuming that you're not going to have issues loading that. Then our next chunk here is that my theme map object that we've been using in the last few exercises. So this is just setting the themes of how we want our plots to look like, and then we can just call that object. So make sure you run it. And now the next step here is if we want to combine all this data into one object, we have to bring each individual layer back, right? So let's go ahead and start doing that here. So the first one, so we're going to bring basically the spatial temporal yield stability zones. We're going to bring the terrain variables and also the soil electroconductivity apparent in two different layers. So the first one here I want to bring in is the spatial yield temporal stability classes and assign that to this object sty underscore v. The underscore v is just to denote that is a vector, and sty is just the standardized spatial temporal yield in vector format. That's what that name is supposed to be. All right, so let's give the assignment symbol. So all of these objects that we're going to be bringing, they're all GeoJSON. They're all the processed versions of everything we did until now. So what is the function that we're going to need for that to bring those data in? If
Read that.
grid SF, right? Yes, thanks. Was that Marco?
Yes.
Thanks, Marco. Yes, so read SF, right? So they're all GeoJSON. So read SF is what we need here. So this layer specifically, it's on the 07 yield monitor project. So let's start giving the path. We have to get outside of code. We have to get outside of the 10 stability project. Then we want to go inside 07 yield monitor, inside of the data folder. And then the layer that we want to bring in is the SY all GeoJSON. So this one right here, SY all GeoJSON. If you run that and you print it, you're gonna see that we have here, so first off, 4,046 rows of data. And then we have the standardized yield for 2017, 19, 20, the mean pixel, the standard deviation of the pixel, the CV of the pixel, and then finally the classification, the spatial temporal stability classification, right? So this is something that we did in a previous exercise. You're probably familiar with what happened there, but I just wanted to remind you. All right, so the next one is we're going to bring our terrain object. We're going to use again readsf because these are all GeoJSON. Now we're going to navigate to the 08 terrain project. So we need to get outside of code, outside of data stability validation project, go inside of the 08 terrain, and then inside data. And then the layer that we want to bring in is that terrain underscore v dot geojson. That's the one that we processed and exported. So once you bring that, you can go ahead and print it. And we have or at least on my side, the number of cells is not matching fully. I have maybe 200 fewer cells on the terrain. And I think that's okay. We're gonna check it later, but I think that's okay. And now the next one is going to be our ECA data or electroconductivity data. Let's give the assignment symbol, read SF again. We're going to get outside of code, get outside of 10 stability, and then we need to go into the 09 soil EC. That was the project. Go inside of data, and then bring in the ECA underscore v dot geojson. That's our processed electroconductivity data frame. Run that and you print it. We have again 3,848 rows, which is the same number as what we have here on the terrain ones. So same number as there. Both of them are a little bit fewer than the yield one. To tell the truth, I was expecting for them to be all the same. So I'm not quite sure what's going on here, but maybe we'll get to inspect that a little bit. All right, so the next thing then is I want to bring oh, you know what? Let me just take one moment here. Let's just check that all the CRS are the same. So here on the standard, the spatial temporal yield stability, it is NAD3, UTM zone 60 north. On the terrain, the same thing. On the ECA, the same thing. So they're all matching. That's what we want, right? Remember, we always want all of our layers, given project, to have the same CRS so they all line up correctly.
In my case, it is the same number of row in between the different SF files.
So you have
And it's the same case for me, all are the same.
all three with the same number of rows.
Yes.
Yeah, that's what I was expecting, to tell the truth. And you know what? I think I know what may have happened. I think maybe so maybe on my side, I actually, the spatial temporal yield stability, I think I just copy mine from last year rather than redoing this year with you all. So maybe that's why they're different. But yeah, I really was expecting for them to be all the same because we use the same grid, right? So if in your side they're all the same, great. That's what we want to see. That's what I was expecting. I think on my side they're not because I copied my SY all from last year when I had a different layer, a different boundary. Whereas I did this year's terrain and EC. So I think from on my side that's the mismatch. Which actually, now that I think about it, I think I on my side I'm gonna have issues when we do the spatial join. I guess we'll check on that soon here. The next thing I want to do here is bring our boundary. So let's use read SF. And then we need to get outside of code, outside of 10 stability. Oops. Go inside of 0.5 digitizing. And then inside of output in this case, and then get our boundary.geojson. So if we print that, this is in WGS 84. So just to make sure that it lines up with all the previous layers, we're going to change that. What function do we need here?
It's ST transform.
Yes, thanks, Polly. ST transform, right? So let's go ahead and do ST transform. I don't expect you to remember the CRS values fully. So this is 6345 is the one that we want here. So if we run that again, that is changed now to ETM zone 16 north. All right, so now we have everything here. We're gonna do this join, but really I think it's, sometimes I make some errors and mistakes, and I think it's also good because I can show you how I would troubleshoot. So on my side, I think that when I do this join, and I believe I left you the entire code already, but when I do this join, I think I'm gonna have issues because I have the different number of rows on my stability, yield stability layer. But anyways, I don't expect you to have issues on your side. So just to walk you through what the code is doing, we've already done this in the past, so it's nothing new to you. But we're starting off with the spatial-temporal yield stability. We're then doing a spatial join with terrain and changing the join type to be ST equals. This is important because they all have the same grid cell, so they should all line up, should all be the equal overlap. And then joining that with ECA. And then finally, I'm just using this function called relocate to make sure that I'm relocating the geometry column to be after the last column. That's pretty much what this is doing. So if you run that and you print it, okay, I have 4046 here. So you can see that on my side, because I started off with the spatial-temporal yield stability layer, and that one had more rows in my case, then the final product also has the same number of rows. But I am kind of curious to see if that actually made sense. So although on your side, I don't expect you to have had issues if all three layers have the same number of rows, on my side, I'm not sure. So I'm gonna check. The way I'm gonna check that is, let me bring a new chunk here. Let me see if I already loaded map view. I have not. So let me include map view here. Now, let me actually create an interactive plot to check on my side. So what I want to do is do a map view first of that STYV. Let me run that and see it through. I can zoom in here to really see my cells. And now I want to, well, let me change the transparency. I think here transparency may be alpha. So I think alpha regions is the name of the argument. So alpha regions, let me do 0.6, 0.5. I don't know if that worked much, but anyways, I'm gonna add a, I don't know, I think we did this maybe 1 or 2 times, but if we add a plus after a map view, you can basically call another map view in another layer. So I'm gonna call here terrain V. I wanna have alpha regions equals to 0.5, and maybe if I remember well, let me break my code a little bit. Thinking maybe color regions, maybe. Let me change that to yellow. Let's see if that works. Okay, so I guess my argument didn't work fully, but you can see there's a mismatch on my side, right? So
Yes.
yeah, and this is not what we want. So on your side, you do not want to like if you follow this, I just did this kind of if this was not in the plan of this class, I just did that to check on my side. And if you checked on yours, you should see them exactly right. Like they should be overlapping completely. So if you were to let me see, let me just do a quick help here on map view because I want to remember what's the argument to change the fill of the coal regions. Okay, so not color. Coal and then alpha regions. Alpha regions was right. So let me do coal regions and have the color to help us also see that they're different. Okay, so now it's a little bit easier to see. So we can really see that they are not matching, right? Especially if I turn one of them on and off, you can really see that they are offset. If you all did this on your side, I would expect you to have them matching. For example, if I do my terrain and my EC, so ECAV, these two layers, so EC now is going to be blue and terrain is going to be yellow. These two should match on my side because I did them this year and they have the same number of rows when I import it. On your side, they should also match. So as you see here, my two layers that I did create this year, I cannot even tell that there are two layers because they're all completely overlapping, which is great. And if you turn on and off, you're going to see that they fully overlap. This is what we need, and this is what you probably have across all of your 3 layers. I don't. Um, so you know what? I think I'm actually gonna have to fix this on my side, which means I'm gonna have to rerun the script that I used to create the STY layer. Let me try to see here because I maybe on my side. Oh, you know what? I think that may take more time than what I'm willing to spend in class. So for now, I'm going to ignore it. But I do want to make a huge parenthesis here and say I'm going to ignore it just for time's sake. But after class is done, I will go back and rerun all my layers and make sure everything has the same number of rows and make sure everything lines up correctly. Because that's what the way it should be, right? And the way that on your side, I'm assuming it is. So maybe let me just ask, did the 3 layers not have the same number of rows for someone? And if that's the case, that's fine. You don't have to worry about it. I just need to know to be able to help you. Okay, I'm not hearing anything, so I'm assuming they all matched. In case if for some reason they would not have matched, you would need to see what is the correct number of rows, and that would you will learn based on the grid, right? So we know how many cells the grid has because we're using that same grid to interpolate, and that should be the same number of rows you should have across all layers. Again, on my side, I made a mistake. I'm gonna fix this after class, but on your side, you should have all 3 layers with the same number of rows, and they therefore will line up if you did this test here that I just did. Okay, so again, assuming that everything is correct, on your side. After we've made the join, I mean, we can even actually come here on this map view. I'm gonna create a new one, a new chunk for us to look at the map view of the joined object. So the name is all v. For now, we can just run that by itself. So on my side, still looks, the all v is the final product, so it still looks okay. Probably what happened is whenever a given cell was not overlapping with any other cell, like what we saw on my case here before, maybe that cell just had an ace, I'm guessing. But anyways, I still get a layer here, right? So let's say now that I have this layer, all V, you could even color this by any of those columns. So if I print all V here, notice that we have so we have 14 columns now. All the columns related to the standard, the spatial temporal yield stability, all the columns related to the terrain exercise, so elevation, slope, aspect, full direction, and then both of the ECA columns as well. Oh, I think I actually have a lot of an ace, maybe only an ace on my case because my join didn't work. Let me actually check that using a summary function instead. Yeah, notice that, so my first layer here, the STY is still working, but all the others are just all an ace because they did not find a match. There was no pixels that fully matched across different layers. So I'm in trouble, and I think Niva is actually helping me out here. So let me check what she sent me. Thanks, Niva. Okay, so Niva shared with me all the layers. I'm gonna use, let me just do that because I realize the way I'm doing here, I'm not gonna be able to show you the exercise on my side, even though on your side it's gonna work. So let me quickly take here the layers that Niva is sharing with me, and I'm going to edit my code just to make that work. But again, this is just a workaround. It's not the ideal situation, but you all have the ideal situation. So that's what matters. So Niva, share with me the layers on Teams. I'm just gonna move them into the data folder here, and then I'm gonna use them. Thanks, Niva. Let's see. So I'm just downloading the ones that Niva is sharing with me. And I'm going to use them. The ideal solution would be to go back and really redo the correct ST or spatial temporal layers. Thanks, Niva. Appreciate it. All right, so again, on my side, I'm going to make some changes. You don't have to do on your side because you already have it ready and good to go. I'm just going to change the layers I'm bringing in to be the ones that Niva share with me. Data STY. Okay, so 3973. This is probably the data that Niva did last year, I'm assuming. Terrain 3973, great. Data ECA 3973, all right. And then I'm going to use the boundary that Niva used as well. Okay, perfect. Thank you so much, Niva. You saved the day. So I'm going to rerun the join here to get all that join. Now, all the layers have 3,973 rows on my side. Now, if we do rerun the chunk that I was running before, everything will line up. If we were to add different map views here, they would all line up as expected, as it probably was on your side. Now, before I had NAs for all the cells, because there was no perfect match in space. Now I don't have NAs anymore. I have 0 NAs because all of them merge in space, except for slope and aspect, because if you remember, we had those NAs at the boundary, so that's normal. And then lastly, I just want to adding another chunk just to show you something that was also not part of the original script, but I want to show you nonetheless. So if we bring in the STY, or sorry, the all V is our merge one. We can say zcol equals to any of those columns. So let's say perhaps equals to ST class. It's going to make that map for us of the yield, spatial temporal stability classes. But because now we have everything on the same object, all V, we can really plot any of them, right? So maybe I want to plot, I don't know, maybe let me do here elevation. Right, so we have an elevation map. So again, this is the reason why I wanted us to work with vector geospatial files for this exercise, because you can really see the data set and you can see all columns side by side. You can see like, so this entire row is the same pixel across different data frames, right? So that's the reason why I wanted us to work with vector. We could have worked with raster as well. It's just that the way the raster prints is not as friendly for us to really see all these different relationships. So this is the reason why I wanted to work with vector in this case. All right, so now because we merged all these layers together and we're gonna need to use these layers again in the future exercise, I don't want to just have to re-merge them again. So because of that, let's go ahead and export this merged object to file. So we're going to use a write SF function, right? Because this is still an SF object. We're going to call the all V as our object. And then we're going to get outside of code folder, go inside of the data folder, and then export this as all underscore V dot geojson. And as always, we're going to say deletes underscore DSN equals true. So if you go ahead and you run that, and you check your data folder, now you should have the allv.geojson right there. Okay, so now that we did it, let's do some EDA, right? As we always do, let's do some EDA. So we start off with the summary. We already saw all these summaries before, so we kind of know what's going on there. But just for you, and I guess, you know what, this is actually a good point to make is, so let's say that I was doing my spatial join with a different number of rows across different data sets, which we saw that, I mean, we already talked about why that was, but there was a mismatch in space between the layers, right? So when we did a spatial join using the ST equals join type, let me just go back to that. So the join happened, it did not give me any errors, but I just noticed that something was off when I checked the summary function. And I saw that before, when I still had the wrong spatial temporal yield layer, I had all NAs, completely NAs for everything that was not yield related data, right? So the summary really helps you to see that, especially with these operations that do something behind the scenes, and you don't, even though it did not give you an error, in my case, it was still not doing what I intended, right? So the summary helps you to see that. So if all of a sudden you see a lot more NAs than what you were expecting, That's a red flag. Maybe something happened. Let's check the summary. Let's make some plots. Let's visualize the data and make sure that we understand what's going on. In my case, and I think probably on your case as well, you may have some NAs only on slope and aspect. And we talked about this already. The reason for that is just because slope and aspect, when it's being calculated near the boundary of the field, it is not able to calculate a value because it needs all neighbors around the pixel to calculate. So it gives you an NA because it does not have all neighbors. That's what's going on. But everything else is good. Nothing else, like nothing else here has NAs as we were expecting, right? So everything looks good on the summary side. Okay, so now let's go ahead and create our maps. So the first map I want to create here is going to be the one to show the ST class. And I'm going to rely completely on you all for this code. So let me ask somebody in Tifton perhaps. What should we do here? What function should we start here? Sorry, I couldn't hear it. If you can say again.
You have to write all v ggplot.
Ggplot, right? So let's start with ggplot. Oh, okay. Sorry, so what you were saying, Benedetta, was all v and then a pipe ggplot. Is that what you're saying?
Yes, but you can also write ggplot and use all v inside.
Right. No, this works. So, okay. So what now?
Geom dense, the geom SF.
geom_sf, right? Because we're plotting an SF object. So we already gave the data here. I think this is going to work. We can try and see, and if it doesn't, we'll edit. But I think it will work. So we don't have to say data equals because that's coming through the pipe already. Let's just do an AES. So if I want to color according to the spatial temporal stability classes, what do we need to say here?
ST classes.
So ST class, but what is equal to that?
So equal to fill equal.
Fill, right? So fill equals to ST class. Let's just go ahead and run that and see if it works. Let's print it. Okay, it did work, so that's what we needed. If you remember in the past, I do like to remove the outline color of those polygons because it kind of adds this extra black color that is really not showing us much data. So just to make the plot more clean, I like to, outside of the yes, I say color equals NA, just to inhibit that. Then as always, I want to change to a Verities color scale. So scale underscore fill underscore Verities. We can use D for discrete in this case. If we run it and we print it, this is what we get. I also want to bring in here the boundary. So I'm going to do a geom_sf data equals boundary. And we need to say fill equals NA, so it does not block the data behind it. Oops. Boundary W. Okay, so we have the boundary outline. And lastly, I want to bring in my theme. Okay, so we made the first plot. Looks good. Now let's do for elevation. So let me just tell you this. Go ahead and copy, starting on all V, just copy all that. Come to the elevation map, give the assignment symbol, paste the code, and we're going to have to change one thing here. or maybe a couple things here. Let me ask somebody else in Tifton to help me out. Or maybe let me ask Kiathi. Kiathi, what do you think we should change here to make an elevation map?
We should change ST class to LF_M.
Perfect. Lab_M. We can go ahead and run this and see if it works. Okay, so I just changed that as you told me, and it gave us an error. So it's saying, hold on. So it's giving a different error than what I was expecting. Maybe my LV has a different elevation name. Let me check. Yeah, so mine says LFV. So that's what happened. But you do want to have LFM if that's how it's named on your side. So if we run this and we print elevation map, it gives me an error. So it's saying error in scale fill varieties D. Why do you think that is? And I mean, I'm asking you as in you all, not just Kiathi. If Kiathi has the answer, I'm glad to hear it. But if you don't,
Maybe because it's the discrete, we should not use discrete for LF. Maybe we should use B or C.
yes, that's exactly on spots. So yeah, so elevation is numerical, right? Makes no sense to use a discrete category. So maybe let's try B for bend. Thanks, Kathy, that was spot on. So if we run it and you print it, then we have this. Remember that bend is just a continuous variable that has been put into bins, right? So we could use variety C for continuous if we wanted. You would just see a more continuous flow of the data. So I mean, really, you know, up to you. I want to keep the B for bins, but feel free to choose the C if you wish. All right, so we just made the elevation map. Now let's make one for slope. So just copy the code from elevation, go on the next chunk, give the assignment symbol. Now if I print here all V, and if our goal is to make a slope map, what should we change on this plot? Let me ask Mohit.
Can you please repeat, Dr. Bastos?
So now we want to make a slope map. What should we change? Because we just copied this code from the previous map, from the elevation map, right? I would just copy from here and paste it. So now how should we change this code to make a map of slope?
Oh, so we'll change the fill to slope V.
Right, so at least on my side, it's called slope, but whatever is called on your side, that's what we want to have. That's it. Thanks, Mohit. So we change that to slope, and then I think the scale of varieties would still work for us here. We can just keep that. And this is how our slope looks like. Let's make a few more here. So we just did slope. Let's go ahead and do aspect now. So we give it the assignment symbol. I'm just gonna paste the entire code that we just did above. Paste that here. And now if I want to show aspect, I'm just gonna use the aspect column, right? That's what we need now. So make sure you change your fill to be equals to aspect on this chunk. Go ahead and run it. This is how our aspect looks like. Next is going to be two more. So we're going to do our ECA 30 and ECA 90. You can just give your, or let's just copy the code again if you need to. You're going to paste that. And then instead of aspect on fill equals aspect, you just change that to whatever is your column for ECA. So I think here on this data frame, I have it named this way. On yours, it may be named something else. Just make sure you change to whatever is named on your side. So ECA shallow first. or sorry, I guess I just copied the wrong one. I copied the ECA 90, but this was supposed to be the shallow. So make sure you copy the ECA 30 for the shallow. Oh, I guess I don't have. Let me see here. Let me see my object. Okay, so I think I have two objects with a very similar name. So you should have ECA 30 and 90. On this case, I have two 90s, but I'm guessing the first one here is the shallow, is the 30. And I'm guessing that,
You will do Dr. Bassos.
sorry, can you say that again?
But I have the same as you, like ECA 90X and Y.
Okay,
What?
I think that this may have happened. Let me try, you know what? Let me try to troubleshoot actually. On my side, let me see. This may have happened. Let me go all the way to when we imported the ECA data. Yeah, so it's already happening there. So I think what probably has happened is maybe on that EC exercise, when we were merging both the shallow and the deep, we may have had both of them named ECA 90 at the column. And when you join, it just said one is X, one is Y. Even though the values under them are, I believe the first one is 30 and the second is 90. So the .x I think is the 31. And we can check this as well by, I mean, we could check different ways. We could go to that exercise and check the scripts, which again is a great thing that we're programming because we can, if we find issues, we can trace back, right? It's easy to go back to the code and see what happened. But if we just look at the summary, if you all remember from class, from when we did that exercise, the ECA shallow had a narrower range than the deep. So let's just check the range here. So 0.7 to 8, 2 to 13. Yeah, so I'm pretty sure that on my side at least, ECA 90 DSM-X is the shallow one, and ECA 90 DSM-Y is the deep one. But anyways, the best way to solve this would be to go back to that project, make sure that things are renamed correctly, and then export again, just to make sure you're on the safe side, right? That you're doing things reproducibly. For sake of class, I think it's an okay assumption to assume that the first one here is the 30 and the second is truly the 90, just based on these values and what we know from these layers. So that's what my assumption is going to be. That's how I'm going to continue here. So going all the way down to ECA 30 map, we're going to call that ECA 9, or at least on my side, ECA 90 DSM-X as being the shallow. And because we have this difference, I just want to change the labs here. So I want to add a plus labs, and then I want to say fill equals to ECA shallow. Just so we don't get confused when we look at the plots. Also, let me just break line to make sure that it looks nicer like that. So I just broke line by a /n. Okay, and then now we're going to do the last map, which is ECA 90. So if you come on the previous chunk, you can just copy all that and then paste it. On my side, I'm going to change this to ECA 90 DSM.Y. That's how that column was. But on your side, make sure you use the appropriate name for your data. And then here, I want to change and say ECA deep, so we do not get confused. So if you run that and you print it, this is what you would see. Okay, so I want to take a quick moment and just check if everyone was able to create all these maps. All right, so, oh, sorry. Was somebody saying something, Tifton?
We're saying that we were able to create the maps.
Okay, thanks, Polly. All right, so now we're basically, I think I may have told you in this class about this package, right? That we've used before, the package patchwork. So what we're gonna do here, if you just, I'm not gonna run yet because I want to show you what this means. Every time we use a plus on patchwork, normally that adds a plot on the same row. So what we're doing here is we're adding the spatial temporal map and then both the CA shallow and deep in one row. And then when you use the forward slash, this basically means break line. So we're getting another row where we have elevation, slope, and aspect. So if you run that, you should see 2 rows of plots and 3 columns like this. Here in R, it does not look the nicest. So the best way for you to really understand how this looks like is to export a file and then inspect on your PNG file and see how that looks like. And then if you want to change your width and height, you can change here and then check again on the file itself. So go ahead and run the ggSave so you can export the file. If you go on the output folder and click on that all maps that we just created, you should see something that looks like this. Again, if you did not like the way it looked as far as like the size of the maps and so on, what I would do is come back to R and just play with the width and height here and run it. And then again, inspect on the file itself. That's the best way to make sure that it looks nice. But I think it looks okay, right? It looks okay with what we're seeing here. The size of the fields and the legends, I think they all make sense. All right. So basically we just made all these maps. So we brought in all those layers, we made the join, we made the maps to visually assess them. And so let me ask you this, and I'll ask to everyone first, just as an open-ended question, and then you can help me to interpret. So I will call a few of you to help me out here. So if you just visually at this point assessing. So imagine that we're trying to explain our spatial temporal stability classes with all these layers. Just visually, are you seeing any patterns of variables that perhaps are correlated with our temporal or our spatial temporal classes? Let me ask somebody in specific. I think I have not, oops, let me go back here. I think I have not asked Luke yet today. What do you think, Luke?
Just looking at I was looking at the ECAs, and it seems there's a pretty good overlap. On the right side of the ST class map there, you can see that area where there's a lot of the teal and the yellow for low, stable, and unstable. On my screen at least, it's a little different on yours actually. But on mine, I kind of see some overlapping with low ECA values, both in the shallow and in the deep maps. You can sort of see it on yours, but it's easier to see on mine, especially for the deep.
Awesome. Perfect. And so EC again is, in this case, we're assuming it's related to soil texture, right? So what do you think that means in terms of that interpretation, Luke?
You would say if the ECA is lower there, you would say that there's like less clay, like a less dense soil or texture. Or yeah.
Right. And then that's related to unstable and low stable points, right? Yeah, that's really that's a great comment. Thanks Luke for sharing your thoughts. Yeah, I totally agree with that, right? So we see, and some of these patterns we have been visually assessing, right? So there was a question in the midterm that you all talked about elevation and its impact on the classes or relationship with the classes. So we're really seeing here, maybe just complementing what Luke was saying. As he was saying, it looks like on these places where we have unstable or low stable, we also have lower shallow and deep EC. I agree with that. That's something that looks like that to me as well. Um, Yeah, I don't know if we could say that there is perhaps a little bit of a signal between low slopes and high stable, potentially, right? So we see here on the slope map, all these dark values are low slope, and we tend to see a little bit more of the high stable on the same areas. So maybe there's something there about slope and how the stability classes are going on. Well, and then slope and aspect are coming from elevation, right? So elevation has some relationship as well. So most of our low stable and unstable are happening under low elevation, right? So this kind of helps us to paint a picture of what could be some potential reasons why these yield classes are what they are. And of course, something to keep in mind as well is here we have, so the electroconductivity layers are related to texture, which could be related to water and nutrient holding capacity. And then we have elevation, slope, and aspect, which are mostly related to perhaps water movements and nutrient movement across this landscape. So those are some layers. They're not all of them, right? Perhaps this field has a pH problem, and we don't know because we don't have that information. Perhaps it has a phosphorus or potassium problem, or perhaps has a nematode problem, perhaps has compaction problem. None of that we are talking about here. So what I'm trying to say is by no means I'm saying that all these layers would explain everything about yield because they are not, right? They're just some of the layers that are very common in precision ag that may be able to help us understand some of the yield limiting factors of this field. But by no means they are the only layers. We have many other layers that could also be used here to help us understand. So I just wanted to make that point very clear. Okay, so basically what we're going to do next is going to be to validate our yield temporal stability, spatial temporal stability classes. So what do I mean by validate? Basically, imagine that so I'm going to be saying some things here that I'm assuming you all have some familiarity with. If I say something that makes zero sense, let me know. I'll be glad to take a step back and give more details about the explanation. But what we're going to be doing here is do an analysis of variance with the goal of comparing the means of these different classes. So for example, one of the things that we're going to do next is imagine a ggplot. So let's think of a ggplot. You have, let's say elevation. So elevation on your y-axis. On your x-axis, you have the four classes: unstable, low stable, medium stable, high stable. So all the elevation data points that were associated with unstable are going to be together in a box plot. And then all the data points that are going to be associated with low stable and medium stable and high stable individually are going to be in their own box plots. And then we're going to do analysis of variance to compare the mean of those box plots and understand if the mean elevation is statistically significantly different for different spatial temporal classes. So that's the vision that I hope you can have at this point. And then we're going to do that for all the variables. So for the terrain variables, for the EC variables, and explain their changes or how they change for each one of the spatial temporal stability classes. So that's what we're going to do next. So I left you the code here, but basically what I'm doing, let me walk you through it. I'm taking, so maybe you've seen this already on your own, maybe you have not. I don't think we made a lot of this in class yet. But if I make a ggplot and I put st class on the x-axis, the order that's going to show up, like the sequence, so the class on the left and then the two in the middle and the one on the right, is going to be alphabetical. Sometimes alphabetical is the order that you want, that's fine. Sometimes it's not. In our case here, if we were to put these levels alphabetically, they would not be in an order that makes sense. And the order that I'm proposing that makes sense is to have low stable, medium stable, high stable, and then unstable as the last one. Whenever you want to change how the levels of a factor show up in ggplot, this is how you would change it. So you would use the function factor, you would call that same column again, and then you call the argument levels, and then you give the levels in the order that you want them to show. This is what I'm doing here. I'm just forcing that the order to show up in ggplot to follow this order. That's all I'm doing. Then I'm leaving out flow direction because I decided not to show flow direction in this plot here because flow direction is really a class, but it's difficult to interpret because if you remember the positions of flow direction, they're just numbers, so it's kind of difficult to interpret. So I'm going to leave flow direction out. So I'm keeping it out with the select. And then I'm pivoting longer all of the columns that we measured. So everything from elevation to ECA. On my code, I'm going to have to edit this. So let me go ahead and do this. I'm going to run from all V all the way to the select without including that pipe, just so you can see what it looks like. Basically, at this point is at least on the data frame, we just remove flow direction. But what I want to do next is I want to pivot longer all of our measure variables. So from elevation all the way to ECA 90 DSM-Y. In my case, in your case, it may be named differently. So I want to pivot longer. Why is that? Because I want to make a ggplot where I want to make many facets in ggplot where each facet is one of these variables. And as you remember, if I want a facet, I need to have a column to facet by. So I will need to have a column that has all the names of these variables under that column. Therefore, we need a pivot longer. So we're pivoting longer here. And the columns we want to pivot longer are just these here, starting on elevation, going all the way to ECA 90 DSM. I'm going to have to edit these names on my side because I have 11V. If I check my data frame, 11V. And the last one that I have is ECA 90 DSM-Y. So I'm just going to have to change that here to say starting on 11V, ending on ECA 90 DSM-Y. Once we do that, so let me run until that point so you can see it. Now we have almost 20,000 rows of data, but then we have now this column here for name that had the previous column names and a column for value, which had the values that were under different columns before. Now, when I show these, when we make a facet of these variables, I also want those facets to appear in a certain order. The default order is alphabetical, and I don't care for that. I want to be in this order. I want to be elevation, slope, aspect, ECM 30, and ECM 90. So here on the levels, you're going to have to specify the order that you want them to be in. On my side, again, I don't have 11M, but I have 11V, so I have to make sure it shows up there correctly. On my side, I do have slope, I do have aspect. I do not have ECA 30 or 90. If you remember, I have ECA 90 DSM-X as my ECA 30, and ECA 90 DSM-Y as my ECA 90. All right. So once you make those changes, then we feed all that into a ggplot where I put ST class on the x-axis and value on the y-axis. We add a geom box plot to show the box plot. I change the color to Verities. I do a facet wrap by name. So remember that name is this column here. So we do a facet by this column and then just change some things about the theme. So if you're able to make all these small changes on your side on this code, and you just run this whole thing, you should see this. You should see one facet for each one of the variables with a different box plot for each one of your ST classes. Before we move on, let me ask if everybody was able to create this plot, if this chunk worked for you. Okay, I did not hear any no's, so I'm assuming it worked for all of you. So I have a list of questions for you all here. So right now we have box plots, right? We don't have a statistical analysis result yet. We don't have ladder separation. We don't have ABCD to know if statistically they're different. So all the inference we're going to make now, or all the hypothesizing, is just visual hypothesis, right? We're not saying this is more than that or lower than that. It's just visual. But visually, not statistically, maybe let's begin by elevation. And I'm gonna ask each one of you to help me out. So let me begin with Marco. Marco, if you look at the elevation plot here, so just this plot, and of course looking at what is the stability class, which the labels are underneath, how would you interpret this elevation box plots?
I would say that the high stable areas are the areas that have a higher elevation.
Perfect. What about on the lower elevation side? What do you see there?
The areas with lower elevation can have either a low stable or unstable.
Perfect.
Yeah.
I agree with that. So really we can see here that elevation is really helping us to differentiate the high stable, perhaps to some extent the medium stable, but it does not differentiate, at least not visually. We don't have letters yet, but visually it does not seem like elevation can separate low stable from unstable, right? That's an interesting takeaway. Okay, so let me ask Benedetta, what do you think about slope?
For slope, we can see that on average, everything is almost the same, but the medium stables is where the slope is a little bit higher.
Yes, I agree. And it's kind of interesting because I was not expecting that, to tell the truth. I was expecting that a slope would either make something very low yielding or very high yielding, but more likely low yielding. But it's not what we're seeing here, right? So higher slope, we're seeing that is medium stable. Interesting. All right, so let's go to the next one. Polly, what do you think about aspect?
I would say that where the high stable was observed where the aspect was high, and the low low, stable, and those that stable were observed where the aspect was low.
Right. So just so we kind of remember, so aspect goes from 0 to 360 degrees. It's just the direction of the steepest slope, right? The side that slope is the steepest on based on that pixel. So it looks here that on the high stable we have values around 100 on average around 100 degrees. So 100 degrees would be just a little bit more than 90 degrees, right? So if 0 degrees is north, 90 degrees is south. And so 100 degrees is just a little bit southwest, right? So that's the slope that for some reason, when things were sloping this direction, it had a better, it had a high stable yield, at least in this field. Yeah, it's perhaps a little bit more difficult to interpret, but that's how I would interpret this. All right, so let me ask Kiathi. What about, so on my side here, it says ECA 90 DSMX, but this is the ECA shallow. How would you interpret ECA shallow?
We can see that the medium stable ones has the higher shallow ECA,
Mm-hmm.
and the unstable ones were the ones with the least.
The least, right?
Yeah.
Yeah, this is interesting, right? Because if you remember, in Georgia or in the southeast, where we have soils that could have high ECA, but that actually be a bad thing because it just means it has a very high clay content that is even bad for plant growth because it's just so hard. It's like a brick. Um, it doesn't seem like that's the case in this field at least because higher EC is being associated with medium and high stable classes, right? So that's something interesting. And I guess on the deep ECA, which is the last one here, is perhaps a similar pattern, right? Than with shallow.
Uh, may I say something?
Mhm.
So if the ECA is really high compared to the scale there, like it's 0 to 8, right? Then we can expect that to be low stable or unstable. But as we can see, all the four classes had comparatively low ECAs.
Mm-hmm.
Yeah, maybe that might be the reason for, because we cannot actually differentiate between the regions here because everything is below 4 and it's not really that high of an ECA. I think
That's a good point. Yeah, it could definitely be that. So our next step on this script is going to be to actually run analysis of variance. So we're going to run an analysis of variance for each one of these plots, pretty much, and then be able to put letters here and say, this is higher, this is lower, like A, B, C, D, and really be able to tell statistically if there's a difference or not. But that's a good point. And also the fact that, we have a lot of outliers. So these box plots, whenever you have a dot showing up, is because that point is potentially an outlier. We have a lot of outliers here, right? So even on the elevation that seemed to be the best layer to separate these four classes, we also have some outliers, right? So there's also, again, it's a noisy data set, right? We have a lot of variability on the field scale. Also, we don't have all the potential layers that could explain the yield stability, right? So we don't have a compaction layer. We don't have like a potential nematode layer, which could be important in Georgia, especially. We don't have other nutrients. We don't have pH, right? So there's a lot of other things that could also help us explain yield for this field that we don't have. But with the ones that we do have, these are the patterns that we're seeing. Okay, so I think this is a good point for me to give you a 5-minute break. And then after we come back, we're going to actually run the analysis of variance and we're going to have a quick quiz as well. So let me give you 5 minutes here. And then once we come back, we'll keep working on this exercise. right, so our time is finished. So let's resume our exercise here. Okay, so our goal is now going to be to run analysis of variance. As you're all going through grad school, I am assuming that you have an understanding of what that is. If you don't, then we're really not going to be able to walk through that in this class. If that is something that you want more background on or wish to take a class, I do offer another class that we focus a lot on statistical analysis applied to ag, including analysis of variance. You can take that next spring if you wish, and if you're still here, because I teach both my courses in the spring. But I still want to show you how we would do that in this exercise here using code. Although again, I'm not going to be teaching you what this means and how things are, because it's not the goal of this class. But basically, what we're going to be doing is for each one of our field variables, so all the terrain variables, all of the EC variables, we're going to be running an analysis of variance for each one of them, kind of like this. But then we're going to be able to put the ladder separation on each one of these box plots. So for each one of those plots, I guess we can think of them that way, we're going to run an analysis of variance. We're going to extract the ANOVA table to check for significance to see if in fact we can explain ST class with that variable. If yes, if there is an effect of ST class on that variable, then we're going to extract model means. So it's going to be the mean. So let's say the mean elevation for each one of the classes. And then lastly, we're going to perform pairwise comparison of those means so we can do ladder separation. So include like A, B, C, D, or maybe all A's or A, B's, whatever it is, but add the statistical significance of that comparison to the plots. So then we can interpret those ladders in that plot. So basically, so the next chunk, there's a lot going on, and I don't want to overload you too much right now. All I want to say is we're going to be needing some packages that you may not have installed yet, not on this course at least. If you're taking my other course, you probably already have these packages. So one of them is EMeans, and then we have multicomp and multicomp view, per, and car. What I would say is uncomment each one of them, run only that line of code. Do not run the whole chunk. That's gonna throw errors. So run that line of chunk. Once you install EMeans, either comment off or just delete that line of code and do the next one. So multicomp all the way to car. So I'm gonna give you just a quick moment to install those packages on your side. If you have any issues or trouble, let me know. I can help you, but I don't expect that you have any issues. Once you install them, I'm going to give you just a moment here. Then we're going to be able to run the analysis of variance. While you are installing, I just want to kind of narrate to you what each one of these packages are and why we're using them. So the package EMeans is the package that we're going to use to extract model means. So the analysis of variance model will give us the means, and we get that from functions coming from this package EMeans. The packages multicomp and multicomp view are the ones that help us to do ladder separation. So anytime that you've shown on your analysis, or maybe you read on a paper where there were ladder separation separating different means, right? So A, B, B, C, D. That's what these packages are going to help us to do. The package per is going to help us to do iteration. This is another topic that this class is not about. So I'm just going to walk you through when we get to that point, but I do not expect you to learn how to do this on your own on this class, because that's not the goal. And then finally, we're going to use the package car to check on the ANOVA tables that we're going to be looking into. So I guess before we keep moving, I just want to say again, I am not expecting you to, if you don't know yet how to do ANOVAs in R, this is not an ANOVA class. This is not an iteration class as well. So those topics, although we're going to be using them in this next chunk, I'm just very quickly going to tell you what they are and how we're doing them. But that's it, right? If you want to or need to learn more about them, either you can take my other class or maybe another class, doesn't have to be mine, but I teach them these topics in way more depth in my other class. Or you can potentially learn from other sources too, but I just wanted to let you know we're doing them here, but I do not expect you to learn how to do that just from following 10 minutes of code. Okay, so if you were able to install all the packages, all these 4 packages, you can go ahead and load each one of them. So emins, multicomp, per, and car. Before I move to the code, let me just make sure I give you a moment to let me know if you need help. Was everyone able to at least install those packages and load them?
Do we need to use also multicomp view, or multicomp is enough?
So when you are installing, you do want to install both. But
Okay.
when loading, I think just loading multicomp should work because I think it kind of loads multicomp view behind the scenes.
Okay.
Thanks, Marco. Okay, so on the next chunk, we're going to be doing running analysis of variance model, getting the ANOVA table, getting the means, making a plot, adding the ladder separation. All these 5 steps for each one of our variables. And because we could basically do one code, like coding one chunk, all the code needed for one variable, and then we would basically copy and paste and do again for the next variable, and copy and paste and do for the 3rd variable, all the way to the 5th variable. We could do that, but instead I'm choosing to do iteration here in R using the per package and the functions map. I want to walk you through here kind of so you understand what is going on. So we're starting with all V. I'm removing flow direction again, just because again, it's a little bit difficult to interpret flow direction. So just decided to keep it out. We're gonna pivot longer again on the columns starting on elevation, which on my case is 11V, all the way to ECA 90 DSM.Y. I think that's how I had named on my data set. Let me just double check on that. Yeah, ECA 90 DSM-Y. So let me just kind of show you only until here. So if you run only until here, you get almost 20,000 rows of data where we basically pivoted longer the all the field variables, right? So all the terrain and the EC variables. Now they have the previous column names are all under this name column. The previous values are under the value column. Now, what I want to do, because I want to do all those things that I told you. So analysis of variance model, ANOVA table, getting the means, getting ladder separation, all that. For each one of these variables, then we basically need to create subsets of this data frame, right? And you can think perhaps about group by. So I want to group by this column, but then I want to have all the data associated with, let's say, elevation here, and then all the data associated with slope here. So I want to basically separate the data associated with different variables in this data set. To do that, we're going to use the combo group by and nest. You have not seen this yet in this class. You have seen in my other class if you're taking both of them at the same time. But I just want to add a comment right here. So I block the pipe flow right there and I run until the nest, just so you can see what happens. So I stopped right here and I'm gonna print ANOVAs below so you can see what's going on. This is what's going on. So the object ANOVAs, which is what is stopped right here at the nest function, this is what it looks like. So let me just walk you through because this can be a little bit confusing. So what you're seeing right in front of you is a data frame, a tibble, that has 5 rows and 2 columns. Each row here is representing each one of our field variables. So elevation, slope, aspect, and ECA shallow and deep. On the data column, however, it's something that I think you may have not seen before, which is on this cell right here, instead of having a value, this is actually a full SF object. So there's an entire SF object in this cell here, and then another completely different SF object in this cell here, and a different one until the end. This is a little bit of brain twist because it's basically you have a column that each cell is its own data frame. And all that is inside of a data frame, right? You have this data frame called ANOVAs that has a column called data, that each cell is a data frame itself. It's a little bit confusing. And if you're confused, don't worry. But I do want to show you just an example. So if I were to pull out this cell right here on this data frame, so the data cell for elevation, I came here, did ANOVAs $, data. So if I do this, it's going to pull out the data column. And if I want just the first cell of the data column, I do double brackets 1. That's what's going to give me this cell. So if we do that, that cell is a full SF object with 3,973 observations. So it has all of our spatial temporal information, and then towards the end, it has a value. What this value here is all the elevation values for each one of these cells. So this column value for the first row of the data frame that we pulled is the elevation data for all these cells. Now if I pull, so let me print again ANOVAs. The second row here is slope. If I pull out this cell, so ANOVAs data double bracket 2, which is this cell here, and look into that, all the data for the yield variables still the same. What is changing now is the value column, because this value column now is the slope value. So all these values here are different for this second data frame. The same thing if I come back to ANOVAs and I look into the third cell, which is aspect. If I pull the data of aspect, same number of rows, same information for yield variables, but the value column now is aspect. So basically just the value column is what is changing in each one of these data frames to represent the variable name that we're seeing right there. So again, this is iteration, one way of doing iteration in R. I'm not gonna get too much deeper than this. I just wanted you to create some understanding of what's going on. Because now for each one of these SF objects with their data frames, we're gonna run a model, ANOVA table, means, pairwise comparison. We're gonna do all that because we have this nested structure of having a data frame nested inside of a data frame. Okay, so I'm gonna allow the flow to go here to the next function, which is a mutate. So this mutate is creating a new column called mod. And I'm calling the function map here. So the function map is what allows us to do iteration. So this column mod is basically applying this model. So it's an LM, a linear model, that is taking the data frame that is changing for each one of elevation, slope, aspect, and so on, and it's using this formula. So explaining value as a function of ST class. Value, again, is changing for each one of those data sets to represent each one of those variables. So if I add a comment right here to stop the flow there and run until mod, and now we inspect this object called ANOVAs, you're going to see there's a new column called mod. And now each one of these cells is not an SF object anymore. It is an actual LM object. It's a linear model object. So if I were to pull out just this cell here, I'll say ANOVAs, $mod, double bracket 1. This is just a linear model output. But then we just did that 5 times. 1 time for each one of these rows. Now that we have a linear model that we ran, and all of these linear models are different, right? Remember that the value column in each one of these data frames is different. So the linear model here is different from this and this and this and so on. So now that we have our model run, I'm going to create the ANOVA table on the next mutate using the ANOVA function. I'm going to add here the hashtag just to block the flow right there and run until here. So we can inspect now this new column called ANOVA that has the ANOVA tables. So if I print the object ANOVAs, now we have this ANOVA column that has each cell is an ANOVA table for each one of those analysis of variance. So let's just go ahead and do ANOVAs $ANOVA. So ANOVA is the name of the object. ANOVA is the column name. If we just print that without the bracket, double bracket 1, it's just going to print all those ANOVA tables for us. Okay, so I just ran this. So we see the first ANOVA table, ST class was significant. The p-value was significant. On the second one, it was significant. On the third one, it was significant. On the fourth as well. And on the fifth as well. So ST class had a significant effect on all those variables that we were looking at. So if we go back just to the plots to visualize, it means that ST class was significant for all these box plots, meaning that there's going to be letter separation here that is going to be A, B, C, and then for all of the other plots as well. We just don't know what those letters will be yet because we had not created them, but they were all different. Or the effect of ST class was significant for each one of these analyses. That's how we would interpret that. Coming back to the code, I'm going to let the pipe go to the next part of the chunk, which is the CLD. So let me lock the flow right here. So CLD is going to be a column where we're going to be extracting the EM means, the expected marginal means for each one of the models. And then we're going to ask to extract the letter separation as well at an alpha level of 0.05 and adding letters. And then we're transforming that into a data frame and just getting the letters themselves. So let me run until here so you can see the effect of that on the ANOVAs object. So now we have an object, or sorry, a column called CLD, and there is a data frame in each one of those cells. So let me pull the first here, which is associated with elevation. So ANOVAs CLD double bracket 1. This is the output of that. So it gives us the classes. It gives us the EM mean, which is the mean of the model. And then if you come all the way to the right, there's going to be letters. So we can see there's A, B, C, C. If we check the second CLD, which is associated, so this cell, let me show you here, this cell right here, which is associated with slope, it's going to be a different set of letters and a different ranking as well of the EME. So A, B, B, C, C, right? So the letters are changing for each one of the analysis. And that's what we wanted to do. So now we basically we ran an ANOVA, we got the letters, we got the means, and we did the pairwise comparison for each one of our 5 field variables of elevation, slope, aspect, EC shallow, EC deep. So after that, I now want to, so let me print again the ANOVAs here for you to see. Now, remember that we nested first, and then we created this data column, and we did all these operations on the nested version of this data frame. Now, I want to unnest. I want to bring CLD out of this structure and have all the lattice separation on the main data frame and not in a small cell data frame. So to do that, we're going to use the function unnest, which brings out that CLD. We're going to unnest that CLD column only. That's the one I want to bring out. So let the pipe flow go and stop that here on the ungroup, just so we stop there. So if you run this, and now you print ANOVAs, now instead of having just 5 rows, we have 20 rows. And that's because for each one of our variables of interest, so elevation, slope, aspect, and so on, we have 4 classes, right? So high stable, medium, unstable, and low stable. And we have the model means for each one of those classes, so the EM mean, and we have the letter separation for each one of them as well. Although we still have some nested columns, but we unnested the CLD, which is the one that had the treatments, the means, and the pairwise comparison letters. And now that we have all that, I just want to come here and again, just change the order of those names so they appear in the order that I want in ggplot. So on my side is LFV, ECA 90, DSM.x, ECM 90, DSM.y. So if you run all that and you print again ANOVAs, you should still have your 20 rows of data. For each variable of interest, we have that variable, we have ST class, the class itself, we have the means from the ANOVA model and the lattice separation. For 5 different models, we just ran all that. Okay, I know that was a lot of information, and again, as long as you were able to replicate the analysis with me, that's what I wanted you to get from this. I do not expect for you to know how to run ANOVA or iteration in R by yourself just based on this 10 minutes of this chunk. So maybe before I keep going, let me just check in. Was everyone at least able to make this run, to make this get to this point? All right. So why are we doing all this? It's because I basically want to be able to add these letters to those box plots here so we can make inference based on statistics and not just on visual assessment as we were doing up until this point. So if you come to the next chunk here, we're basically now making a plot. And I think all the code is here, so I'm not going to walk you through the whole thing. But really, we're just changing the order of the ST class again to be low, medium, and high stable and then unstable. We're selecting out flow direction. We're pivoting longer again, starting on elevation and ending on ECA deep. Remember, on my side is LFV and ECA 90 DSM.y. Yours may have been correct already. We're changing again the factors of the name column or the order. So LFV, make sure that these are matching yours. And then we're putting that on a ggplot. We're asking for the same geom box plot. We're faceting again by name. So all this is the same. Now the difference from what we did on the previous box plots is that we're adding a geom label to add the label adding the letter. So the letter separation of that analysis. So if you go ahead and you run this whole thing, if you were able to change here successfully, and then these names here successfully, you should see something like this now. So again, I know that this was way beyond what was the goal here. Oh, is today class until 4? Yes, thanks, Neva. I thought we were going to 4:10. So thanks, Neva, for letting me know about the class time. Okay, so let's do this. We're gonna have the quiz next class. But basically what I will ask you to do is to look into these plots and now interpret this plot with the statistics on it and be able to understand the lattice separation and its effect. So this is a great stopping point. So let's go ahead and let me get your attendance. Okay, so please go ahead and claim your attendance. If you were not able to get the code working to this point, let us know. Please reach out on GitHub and we'll be able to help you out. But if you were able to get to this point with all the box plots with the lattice separation, then you're good to go. We're gonna continue from this point on next class, and then validate statistically our different zones. All right, I think that's all I had for today. If you have any questions, I'm going to stick around for a couple minutes. And if not, I'll see you on Thursday.